eigenvalue of the transformation of vector space or non-commutative algebra. I want to consider the method of solving the system of differential equation part 1. In the equality part 1, the conversion of summation over index S is adopted. Before we begin, we consider necessary definitions and theorems. Firstly, let A be non-commutative algebra. When A number B, there exists some algebra CAB of the algebra A such that C belongs to this algebra if and only if C commutes with B. The algebra CAB is called center of A number B. Next theorem. Let A be non-commutative the algebra. When A in A, if C belongs to algebra C, then B of C also belongs to the same algebra for any polynomial of B with conditions from the ring T. And one more theorem. Let A be part as a relativity algebra, and A in C belongs to A. The condition 1.4 implies that equality 1.5 is true. Now we consider the matrix of A numbers. I recall that there are two operations of products of matrices
colors.
algebra A. That the number of rows of matrix A equal the number of rows of the matrix B. Row-column product or RC product of matrices A and B has form 2.2. Here there is some over index K. RC product can be expressed as product of row of matrix A or a column of matrix B. This corresponds to the standard product in commutative algebra. Another definition. Let the number of rows of matrix A equal the number of columns of matrix B. Column row product or CR product of matrices A and B has form 2.5. And CR product can be expressed as product of column of matrix A over row of matrix B. In following definitions, we consider different types of eigenvalues of matrix of A numbers. A number B is called RC eigenvalue of matrix F if the matrix F means B here is RC singular matrix. And column B is called eigencolumn of matrix F corresponding to RC eigenvalue B if the equality to the 7 is true. Similar definition. And number B is called CR eigenvalue of matrix F if the matrix F means BEN is CR singular matrix. And column B is called eigencolumn of matrix F corresponding to CR eigenvalue B if the equality to the A is true. This eigenvalues called singular eigenvalues. Now we consider left and right eigenvalues. Let A2 be square matrix which is CR similar to the diagonal matrix A1. Thus, there exists no CR singular matrix U2 such that equality 2.9 and 2.10 are true. The column U2I of the matrix U2 satisfies the equality to 11. The number BI is called left CR eigenvalue, and column vector U2I U2 is called eigencolumn for left CR eigenvalue BI. Let A2 be square matrix and for which is RC similar to the diagonal matrix A1. Thus, there exists no RC singular matrix U2 such that equality to 12 and to 15 are true. The column U2I of the matrix U2 satisfies equality to 14. And our Bi is called right RC eigenvalue. And column vector u to I is called eigencolumn or right RC eigenvalue Bi. Now we consider linear map of a vector space. Let A be a associative division of the algebra with center T. We can identify linear map of the algebra A and tether linear 1 by the equality linear 2. Here we put argument x instead of tether product. Let linear map A of the algebra A as representation linear 3. Here we assume all index S. And linear map B have representation linear 4. Here we have sum over index T. Then product of maps A and B has form linear 5. You see that we have put this map instead of tensor product, then argument is that tensor product also. The product of maps linear 6, which we are considering right now, can be extended to the product of matrices of maps, because we can represent linear map by the tensor of rank 2. Let Aij be Aj the tensor over algebra A. We introduce RCO product of matrices of maps linear 7, using the equality linear 8. Small remark. Linear map of vector space B or field D is homomorphism of the vector space B. There, we use a matrix of the numbers as coordinate representation of linear map or homomorphism. If we consider vector space B or division of the algebra A, then consider similarity between linear map and homomorphism will be broken. We still use a matrix of A numbers to represent homomorphism of a vector space. However, we cannot confine ourselves to the set of homomorphism to consider linear map, because in this case we will not be able to define a linear map. This is why we define linear map of a vector space V as a linear map of corresponding Z vector space V. Therefore, a linear map for a linear map, it doesn't matter if you consider left or right a vector space. Here, let V1 with F, W1, Wf be a vector spaces, and V is the sum of vector spaces Vi. W is the sum of vector space Wi. Let us represent V number V as column vector linear 9, and we represent W number W as column vector linear 10. Then the linear map F of vector space V in the vector space W whose representation is a matrix of maps P11, such that if W is image of vector V, then we have equality with 12. The map Fij is a linear map and is called partial linear map. Let V be left a vector space of columns in dimension F, and E be base of a vector space E. For any I, the set AI is equal A times EI is a space of vector space E. And vector space E is the sum of vector spaces AI equal to P15 or P14 of right vector space. Linear map F of vector space E is called linear transformation of a vector space. According to considered right now theory, linear transformation of vector space V has form P15, where the map Aij is partial linear matrix. Now we consider eigenvalues of this linear map. A number is called here RCO eigenvalue of the matrix F if there exists column vector V such that equality ordered 1 is true. The column vector V is called eigencolumn Fourier RCO eigenvalue P. Similarly, a linear map back is called right RCO a number P is called right RCO eigenvalue of the matrix map of maps A if there exists column vector V such that the equality for the two is true. The column vector V is called eigencolumn for right RCO eigenvalue V. There is a relationship between different types of eigenvalues. We, for example, consider one of them. Let entries of matrix A satisfy equality for that V. Then let RCO eigenvalue V is yet CR eigenvalue of the matrix A1. The equality for that phi follows from the equality for that V. Then equality for that 6 follows from this equality. We have here pi capital, here little d. The equality for that 7 follows from the definition for that 1 of real RCO eigenvalue of the matrix A. The equality for that 8 follows from the equalities for that 6 and for that 7. Because we see we have on this side the same product of the matrix. So this product equals this product. The theorem follows from the equality for the A and from the definition of the real CR eigenvalue of the matrix A1. Now we consider one more theorem about eigenvalues. Let the column vector V of V eigencolumn for real RCO eigenvalue P in the matrix A, and number B satisfy the condition for volume D. Then for any polynomial pair of X with coefficient from the ring D, the column vector CV where C equal P of P is also eigencolumn for real RCO eigenvalue P. Similar theorem. Let the column vector P be eigencolumn for right RCO eigenvalue P of the matrix A, and A number P satisfies the condition for volume pi. Then for any polynomial P of X with coefficients from the ring D, the column vector BC, the order of little different, where C equal Q of P is also eigencolumn for right RCO eigenvalue P. Now we are ready to consider system of differential equation 5.1. We see that the coefficient on the both sides of the function that we search. We can represent this system using product of matrix in the form 5.2. Let a number P be real RCO eigenvalue of the matrix A and satisfy condition 5.3. Then the system of differential equation 5.2 has solution 5.4, where a number C satisfy condition 5.5, the same condition for eigenvalue P, and the column C small is eigencolumn of the matrix A corresponding to the real RCO eigenvalue P. Similar theorem. Let a number B be RCO eigenvalue of the matrix A and satisfy the condition 5.6. You see the y coefficient, this little different conditions. Then the system of differential equation 5.2, the solution 5.7, where a number C satisfy the condition 5.8, and the column C is eigencolumn of the matrix A corresponding to the right RCO eigenvalue P. There is no other solutions of this system of differential equation. Now we consider differential equation 5.9. I remind that we put the derivative instead of tensor product. Let a number in X equal exponent of pt be solution of differential equation 5.9. Let a number p is a root of the equation 5.10 and satisfy either condition 5.11 or the condition 5.12. Now we consider example how to solve this differential equation. The differential equation 5.10 is equivalent to the system of differential equation 5.14. The matrix representation of the system of differential equation 5.14 has the form 5.15. We have yet to find a method for determining eigenvalues of the matrix 5.16. I expected this maybe this year or next year. I'm not sure how it will go research. However, according to the theorem 5.3, eigenvalue of the matrix 5.17 are roots of the equation 5.18. This equation has two roots, x equal I and x equal j. You consider both solutions. The value p equal I satisfies the condition 5.3. According to the theorem 5.1, we look for a solution in the form 5.20, where C0, C1 are real numbers, and Ci satisfies condition 5.5. The column Ci small is agent column of the matrix A, corresponding to the real R0 eigenvalue E equal I. According to the theorem 1.2, 1.3, that we considered in the beginning, the equality 521 is true. And the equality 522 follows from the equality 520 and 521. According to the theorem 4.7, the column Ci small, is agent column of the matrix A corresponding to the real R0 eigenvalue E equal I. Since for us, it does not matter the format of notation of agent columns of matrix A, we can represent the solution of system differential equation 5.14 as 5.20p. The equality 524 follows from equality quotient 4.1 where b equal I. So equalities 25.26 follows from equality 5.24. That's the product of matrices. And the equality 5.38 represents this product of matrices. The equality 26 follows from the equality 25 because you see your second term cancel right side and the rest term are just equality 25. Therefore, the solution is 527, where you put the I equals 1. It remains to check that this solution satisfies the system of differential equation. Now we consider second rule. The value b equals j satisfies condition 5.6. And according to the theorem 5.2, we are looking for solution in the form 30, where C0, C1 are real numbers, and Cj satisfies condition 5.8. The column Cj small is agent column of the matrix A corresponding to the right R0 eigenvalue E equal j. According to the theorem 1.2, 1.3, you have equality 521, and the equality 522 follows from the equality 530 and 521. According to the theorem 4.8, the column Cj capital is agent column of the matrix A corresponding to the right R0 eigenvalue E equal j. Since for us, it does not matter the format of notation of agent column of matrix A, you can represent the solution of the system of differential equation 5.14 in the form 5.23. The equality 24 flows from equality order 2 where B equals J. And equality 35 and 36 flows from the equality 34 and the equality needed 8. The same, the equality 36 falls from the equality 25. Therefore, the solution is 27, where we set that J equals C1. It remains to check that we get solution of the system differential equation. Therefore, general solution of the system of differential equation 514 is 529. You see that we put exponent on different sides of the column vector. The general solution of differential equation 518 has form 540. The final remark. Plot and division of polynomial in non-commutative algebra are not simple operation. So or suggested to consider left-sided or right-sided polynomials. Only find product of left-sided polynomials in such a way that the result of the operation is left-sided polynomial. Or also propose a method of transformation of polynomial into left-sided polynomial. This algebra is called Euler polynomial theory. Method for solving the differential equation 515 raises the question of the limits of applicability of Euler polynomial. Because we cannot find both roots of the equation 518 by transforming the polynomial 518 into the left-sided or right-sided polynomial.
Is that it?
Yes.
Okay, very good. Thank you. Thank you. Does anybody have any questions?
Just one second. Okay. I've been considering the case of roots for a while on quaternions for polynomials. Do we know if the conjugate root theorem holds for the quaternions?
I don't hear properly. Can you? I didn't hear properly your question. Sorry.
The conjugate root theorem says for the complex sums that if I have a polynomial of degree n, let's say even n.
Complex numbers?
Yes, that you will have, the roots will always be conjugates.
The problem here that I said roots not complex numbers, these roots are quaternions.
Yes, I'm asking, I just wanted to know, because I've been looking for the answer myself. Do we know if the conjugate root theorem holds for quaternions?
I don't understand the question.
Do we know if the conjugate root theorem holds for quaternions? Do we know if the conjugate root theorem holds for quaternions? That's what he's asking. Do we know this yet?
Can you give example of the question?
Yes, so if the conjugate roots, for instance.
Conjugate root?
Yes, conjugate roots of a polynomial.
No, probably I didn't work in conjugate root because if you mean on paper that I wrote in 2010, I tried to solve the system of linear equations for complex number, which considered not just complex number, but also operation of conjugation. And this involves using of quasi-determinant. This is a very good idea because what happens when we try to solve a system like here for quaternions, it's not a good idea to use directly this method using tethers. But at the same time, I found that I can consider a set of linear maps not like set of tensors, but also like vector space or quaternion algebra. And it has in the base 4 maps.
Next speaker.
Just identity map and 3 maps of conjugation. And I think using this way, I can write quasi-determinant, which considers only quaternions. And this probably will help to solve a system of linear equation in quaternion algebra. And also probably will help to find the condition when I have eigenvalue for linear map. Did you answer your question? Or?
Yes, I'll talk more later, especially about systems of linear quaternion equations.
Yeah,
I have
because
a lot to say about that today.
yeah, because I need to use this configuration, but I yet not. First, my attempt was failed, but later on I realized that because I choose system with a singular matrix. This is a very interesting case because you need to know. Because when you have a singular matrix, the solution might be only one or infinitely many.
All right, thank you very much. I hate to cut you short. You can email him though, and get in touch with him. Thank you, Alex. Thank you so much. I also have some questions for the talk. Thank you, Alex. That was great.